Let's start with hash. So we're already familiar with dictionary and what it means, right? It's just key value pairs, right? Here, key is going to be unique. So what are the operations? ADT means first you have to ask operations, right? We have insert, delete, and search or get, right? So before we jump into this, let's see what we already know, right? So till now, for general search, best solution we have till now is btrace with O of log n base m, right? Now we know that um, for array, search is O of n linear search, right? That is, if you do not know the index, basically you have to search for it. Now, what if you already know the index? Then you just have to perform this one thing, O of 1, when you know the index, and that will tell you whether the element is there or it is not there. So the goal here is, what if we had a way to compute this index for the array. So whenever you insert, you're gonna be computing the index. So that is how we're gonna deal with hash. So we're gonna do this using something called a hash table. What goes in here? So general concept is you have your key, and then there's gonna be a function f of k that is going to take in this key, perform some function on it, and it's going to return some value that is going to be your index. This is basically what you call a hash function, right? It is going to map all possible values of keys through this function to a range of indices, right? So what happens here is, um, since you have to do this at insertion and for search, right? Uh, so you take the key, you pass it through the function, and then you get the index. You place ARR of IDX is equal to value, right? So that's how it's going to go. So the time complexity of any of these operations is going to depend on this hash function. So time is dependent on um, hash function. So what we usually do is, since this is a function we can take on our own, usually we take it as we take it at time of O of 1, so that general complexity we can still make it as less as possible, right? Let's take one example. Um, let's take a hash table size 10, right? So this is just going to be an array of size 10. I'll put the indices on this side, and then the values are going to go here. And whenever you do this, you have to define your hash function. Here I'm taking it as mod the size, right? I will insert 7. So what I'm going to do is to find where this is going to be inserted, I will perform h of k, which will be 7 mod 10, which is going to be 7. So at this index, I'm going to place this value. I'm taking key value as the same here, just to simplify things a little bit. And then let me insert, say, 14. H of k is going to give you 4 here. I'll put 4 here. 14. The value is 14. And then if I insert 23, it's going to map to index 3. So 23 is going to be here. Right. So uh, let's see. Let's talk about collision. Now we had a bunch of input, right? This is your input space. It is it's much bigger than what h of k will map it to its output space. Now, um, since this is greater than output space, it's gonna take many to one mapping. So what this means for us is multiple keys can map to the same hash value, right? So key 1, key 2, you pass it through hash function. It may land you at the same index. So this, as you can see, is obviously a problem. How can you have two different values mapping to the same thing, right? So we have to solve this using some collision resolutions. Now let's take the same example. Um, let's say I want to insert 27, right? I will pass this through hash function and I am going to get 7 again. There is already a value at 7. This is a collision. Uh, okay, resolution we will see later. Let's look at some other terms. Now, load factor. Load factor, okay, it will need um, two things. N, which is the number of filled spaces, let's say, by M. This is the total number of spaces available. Right. So, as the load factor increases, your hash table is going to become more and more full. And yeah, as alpha increases, likelihood of collision also will increase. Right. So this needs to be maintained in an equilibrium. If this is too low, then you're gonna waste space because it's so sparsely populated. If it is too high, you're going to get collisions. So we are going to have to maintain this also in a proper value. So let's get back to hash functions, right? What makes a hash function a good one? It has to follow three criterias. One, it should be easy to compute. That is, since this is going to contribute to your overall time, we want this to be often. And then it needs to have a uniform distribution. It shouldn't favor some uh, hashes more than others. And then you want to minimize collisions. Right. So these three are things we want to keep in mind when selecting a hash function. Now, let's look at some hash functions. Uh, let's take a not very good one, identity. This will just h of k equal to k. As you can see, obviously this is very bad. This will probably lead to a lot of space being wasted if you're just mapping it directly. And this is just a bad hash function. Let's take divisive. This is when we take mod h of k is equal to k mod m, where m is the size of hash table. Uh, so for our examples, we use this because it's a very basic function. We can have a multiplicative hash function. H of k is floor m into ka. A we are going to choose mod 1. This will give you in the range 0 to 1, where uh, a belongs to 0, comma 1. For ideally, we would take A is equal to golden ratio. This will lead to less collisions. And then we have something called universal hashing. Right. So what it does is there is a family of hash functions. It will choose one of these at random, and then it will work with this. So what this does is, if there is like some like kind of if somebody knows your hash functions, it's very easy to know which inputs will give you collisions. What this does is ensures that like you can't target the hash function this way, right? That is hash function. Let's go to the operations. First, we have insert. We've already seen this. So you just uh, compute hash, um, and then assign the value here after checking for collisions also. Right. That is basically what insert does. We've already taken the example from before. I'll just copy that over. Right. Then we have delete. Uh, this also, it will just same thing as this, and then it will remove the value. Right. So if you're going to remove 14, you just compute the hash for this. You will get it as 4. Go here and then delete this. Right. And then you have search. Now here is also the same thing as before, just compute hash, see collisions, and then arrive at wherever you need, right? So if you wanted to search 23, you'll pass this through the hash function, you will get 3, you will go to 3, and you will see that 23 is present here. If say search 16, this will give you through the hash function, it will give you 6. You go to 6, you do not see the correct value here. So this will tell you that it's not there. So let's just look at the algorithm. Um, so let's see some things about the complexity. So what happens here is we want to have the collisions as less as possible. And worst case collision resolution still remains to be O of n that we have taken, right? But in most cases, it's going to be O of 1. So what we say this is called amortized. So we're just gonna take it to be O of 1 in most cases and in the best case. In the worst case alone, we are going to take this, right? So what happens here? You get the hash by passing the key to the hash function, and then you calculate the index from the hash, and you check if a value is there, and you see if the value is your correct one. uh, right. And then you just add the element. Otherwise you have to resolve the collision, right? So after collision resolution, you have to still map it, and then you have your value added to the hash table. Uh, so hash function, we are going to take O of 1. Mod is also O of 1. All these checks are also like constant time only. This is also 1. Equality check here also 1. Here 2. As you can see, um, only this part is we are concerned with. That's what defines the complexity here, right? So that's why we have these lines here. Deletion also, same case as insertion. You just have to take out the value. That's all the difference, right? Here, um, also same concept applies. You can still see everything is still O of 1. This is only the thing we are concerned with.
So collision resolution. One minor correction to what AJ said. So at the hash table entry, you have both key and value. You also store the key because the key is how you know if there is a collision or not. If you only store the value, you cannot tell if there's a collision. Uh, so what happens is you compute the index, and to check for a collision, you see if the keys match, if the key you're searching for and the key at the given index match. If they match, you don't have a collision. If they do not match, you have a collision, and you have to perform a collision resolution. Right. Now, there are three major approaches. I'm going to talk of two in the beginning, and we'll get to the third one later. open hashing, and closed hashing. Open hashing allows you to store multiple key value pairs at the same index. Multiple per index. Closed hashing limits you at one per index. Right. So there's only one open hashing method, which is simple chaining. Excuse me. Separate chaining is an open hashing method. What you do there is you take a hash table and in the hash table, each element just contains a linked list. Just null initially. Okay, let's say we insert 7. 5 mod 7 is, oh, sorry, 6. 7 mod 6. 7 mod 6 is 1. So 7 goes here, in which means you just add it to the linked list. Let's say we add 1. We just add it here. And then if you add 13, you would add it here. And similarly for other places. Say you add 2, then 8, right? 4, 10, whatever. So this solves collisions by just storing a list of elements at each index. So if you run into a collision with the first element of the linked list, you just have to keep looking down the linked list until you find the element you're looking for, right? So solves collision, but introduces clustering. So what happens here is, say all the elements are I insert are uh, 1 mod 6. So say all the elements I insert satisfy this property. Then all the elements would be inserted at index 1. In that case, this essentially becomes a glorified linked list, right? Whatever element you are searching for, it's always going to be at index 1, and you have to run through the linked list until you find them, right? So it makes it worst case open. And the load factor can get incredibly high. greater than 1 is possible. This is the only hashing mechanism that you're going to see where the load factor is greater than 1. This is because allows more than one node, one element, one element per entry or per index in the table. Since it allows more than one element, what happens is you can overload the table beyond. There can be more elements in the table than there are indices, right? So these are the disadvantages caused by separate chaining. In the worst case, you get O(n) access. So let's look at the alternatives. The second option is from closed linear probing. Pretty self-explanatory. You are going to probe for empty indexes linearly. So let's say we have a table. Okay, let's say we have the indices 0, 1, 2, 3, 4. We're doing what 5 time. Cool. Let's say we have inserted 2 here and we want to insert 7. 7 mod 5 is also 2. So in that case, you just continue down uh, the table until you find an empty index. So you just insert 7 into the next empty index, right? Let's say we want to insert 8. Now 8 is 3. 7 already occupies that spot. So you linearly probe again. Let's say we want to insert 3. You check. You can't insert 7's already there. You go down. 8's already occupied. So you have to insert 3 here. Let's say we want to insert 5. You can't insert it here. You have to insert it here. So you're just going to push everything down. Or let's say rather than 5, we are inserting, see, what's that? 12. If you insert 12, you'd start here, go down, and keep going down until you find the only empty spot. Now the entire table is full. You can't insert anymore. Now let's say you want to search for 12, right? By hashing 12, you get 12 mod 5 is 2. You go look at 2. 12 is not there. So for collision resolution, you do linear probing. You get to 7, not 12. You get to 8, not 12. C3, not 12. And then finally, once you looked at all the elements, literally the last element you see is 12. So linear probing also solves collision. It allows us to find empty indexes if there are any, uh, finds indexes. But clustering is still a problem. Also, see when we wanted to insert 8, the index 3 wasn't available due to collision resolution of a different index. That is also an effect of clustering. So due to clustering, we get O(n), and clustering affects multiple indexes. In separate chaining, clustering only affected the singular index because everything was just pushed onto the same index. Here, it's going to affect multiple indexes, right? Now, let's look at a solution to this quadratic probe. So, unlike linear probing, quadratic probing, you just take a quadratic equation and then use it to find the next indexes, right? So, you would have a equation like uh, you take the original index, mod m, and then you add some constant multiplied by the index square. So you have a quadratic equation, and this addresses the problem of clustering uh, close together. So let's take a bigger table as an example. Zero, two. Here, let's say we have inserted 2 here, 8, 15, 11 here, and 8 here. Then, assuming linear probing here for demonstration, say we have inserted 4 here. Let's see how all the insertions are clustered together due to the collisions pushing things down to the next immediately available index. So, quadratic probing essentially just gets rid of that by pushing it to an index that is a little bit further down. And to push it to an index further down, it uses a quadratic equation. So you would have 11, and if you wanted to insert 8, and you had like something like 3 plus, let's say the constant is 2 times 3 squared and whole mod 8, what would that be? 3 plus 2 times 18 plus 3 is 21. 21 mod 8 would be 5. So you'd insert it here. So you leave gaps. Sometimes, depending on the equation and the current state of the hash table, the gaps might be bigger or smaller, but it allows you to leave gaps in between that reduces the clustering and makes the entries in the hash table more evenly distributed. And when things are more evenly distributed, a random insertion is more likely to have an empty spot. When things are clustered, some insertions will end up wanting to be in the cluster and they'll have to keep searching for an empty index after that in linear probing. So this avoids that, but this introduces another problem. So this quadratic equation, right? This can get stuck in an infinite loop. Let's say that uh, I can't come up with an example off the top of my head, but uh, imagine that the quadratic equation mod 8 only spit out these three indexes. So you want to, uh, let's say there's another element here. Let's just say it's 1. And you want to insert here. And the quadratic equation just keeps spitting out these three indexes, mod 8. So what uh, what that would do is it start here, look, see that it's occupied, go here, see that it's occupied, and then go here, see that it's occupied, and then that would lead back to here. So you can get stuck in an infinite loop like that. So that is a possibility with quadratic probing. And to mitigate that, you have infinite loops. But these loops occur only when table size is composite, that is not prime. So if you take a prime table size, the modulo ensures all available indices are probed eventually. And just in general, having a hash table with a prime size is good. Uh, that's just because when you take the modulo, there are no numbers in between that would give you zero. The You're taking maximal advantage of the modulo operator being there. So it would occupy all the numbers from 0 till m minus 1. Whereas if you took a composite number, there would be any number of uh, cycles in between where it could possibly end up increasing the probabilities of collisions due to there being multiple factors. So that's all the probing techniques we have for collision resolution. The other technique we have is rehashing. This is not a collision resolution technique on its own, but it is used in combination with others to keep load factors in check. Essentially, what you do is when you insert or delete, you do your insertion and or deletion, do collision resolution to find the element, whatever, and then you compute the new load factor with the new number of elements. If greater than maximum allowed, the maximum is determined by us. If it's greater than the maximum, grow table. So you just the standard thing to do is double it in size. If it's lower than the minimum, you shrink table. And now you have increased or decreased the size of the table. So M has changed. So what you need to do is go through all the entries for all entries. Hash again and take mod with new M and insert and collision resolution and everything else. You have to hash all the entries because the size of the table has changed and therefore your hash function has also changed because the hash function is dependent on the size of your table. So this is the resize algorithm. It's not always exactly this, but something like this. So you create an old table and store the old capacity, and you take the new capacity to be 2 times old capacity, and you can optionally make sure it's prime. You can just plain old 2 times old capacity will also work. If you're doing quadratic probing, you have to find a prime size, or you're just to reduce collisions, you can find a prime size. And you create a new empty table of the given size, uh, and you set the size to 0, and then you insert all the keys from key value pairs from the whole table. So let's see. Let's say our load factor is 0.6. 0.6 is our alpha. Then, okay, we have 1, 2, 3, 4, 5, 6, 7. So 60% of 7 would be, okay, 60% of 7 would be 4.2. So at least greater than that. So since we're dealing with integers here, that would be 5. So our maximum threshold is 5. So if we go greater than 5 elements, we are going to rehash. 6, we have 7, say 9, 2, 4, 5, 6, 7. We have 2, 3, 4. Yeah, we have 5 elements here already. So we have to rehash. So we just increase the size of the table by 2. 8, 9, 10, 11, 12, 13. So we have to rehash all the entries now. So 9 mod 13 would be 9. So 2 mod 13 would be 2. 4 mod 13 would be 4, and 5 and 6. Since everything is less than 13, they all just go into their one-to-one mapping with the index, right? 2, 3, 4, 5, and 9. Now the new load factor is 5 over 14, which would be, hmm, let's just say it's about one third. So that's the point of rehashing, to reduce the load factor when it becomes too high to minimize the number of collisions you get. Anything else I have to cover? Yeah, I think that's everything for rehashing. Next up, we have extendable hashing, which is the type of dynamic hashing, which is the third type after open and closed. We saw open and closed hashing. Now we'll see dynamic. So extendable hashing is a type of dynamic hashing. We saw that when the table gets too full, we used rehashing. But rehashing is expensive. We want O of 1. Rehashing is O of n. Extendable hashing solves this by uh, splitting the hash table into global and local bins. So your global bin is just that. They're just pointers to local bins. Initially, there's two global bins and two local bins. Now, each local bin has a fixed size, and they have a depth. So global depth D. D is number of bits. Y number of bits, that is what they use as a stand-in for a hash function. So instead of hashing the value, the global bin just looks at the D LSBs, D least significant bits. So let's take that with an example. And local depth is how much the thing has split. I'll explain it in a moment. So we have a global depth of 1, let's say 0 and 1. Global depth is 1 right now, and local depth is also 1 initially. Let's say we want to insert 2 here. 2 ends with 2 is 1 0 in binary. So insert 2 here because it ends with 0. If you look at the last D bits, uh, right now it's 1 bit, so you just look at the last bit. So essentially, this is an odd even split right now. Let's say 3, 5, 4, 6. Let's say the local bin has a maximum of 3 right now, and we want to insert 8. 8 is greater than the maximum number of elements allowed in the local bin. So you're going to have to rehash. Now, how rehashing works is you try to just split the local bins alone. And since the local bins are fixed size, splitting them is a constant time operation. So you try to do that. For that, these two uh, should have the relation D is greater than L. If D is equal to L when you split, you are forced to split the increase D by 1 bit to accommodate more local bits. Let me just say we have this. So we want to increase this to 2, and we cannot do that while this is 1. So we are also forced to increase this to 2. If the global depth is 2, what that means is we are going to look at the two first two last two significant bits. So this becomes 0, 0, 0, 1, 1, 0, and then 1, 1. Right. So we are splitting this bin. So we are going to have this one bin that ended in 0 has split into two bins that end in 0. So we have another bin here now. So if it ends in 1, 0, it goes here. 1, 0 is 2. 4 ends in 0, 0. 4 is 1, 0, 0. So it ends in 0, 0. And 6 is 1, 1, 0. So it ends in 1, 0. So 4 stays here and 6 goes here. So these two local bins now have a depth of 2 and the global depth is 1. And this bin has not been split. Now we can keep inserting here. Let's say 8, 8, uh, 8 would be 1, 0, 0, and 0, 0. Okay, 9 would be 1. Oh, yeah. In the meantime, 1, 1 bin also links here. So the local bin here is being shared by this and this. So the formula is 2 power d minus L gives you number of global bin sharing local bin, right? So this gives you the number of global bin sharing local bin. If you insert 2 power 2 minus 1, it's 2 power 1 equals 2. So 0, 1 and 0, 1, 1, 1. Two bins are sharing this local bin. And for these two, 2 power 2 minus 2 is 2 power 0 is 1. They are exclusive. So when D is equal to L, it's exclusive. And for each, a difference of 1 doubles the amount of global bins sharing a local bin. Okay, let's keep inserting here. 4, 8, 10. goes here, 12, like 10 goes, 8, yeah, 10 goes there, 12 goes here, 0 goes here, let's see, 16. Let's say we want to insert 16. That case, local depth is 2, global depth is 2. We have to split again. There, what we do is, oops, so now 3, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You have 3 bits, and this bin will split. These two bins will not split. So this bin is going to split into, yeah, it's only 0 is going to be here. 4, 8, 12, 16 are immediately going to the 100 bin. Uh, oops. And this then gets 4, 8, 16, 12, 16.
8 and 16 still goes up.
What?
8 and 16 is still in 0, 0, 0.
Oh, yeah, right. Uh, yeah, 8 here, 16 here, 12 here. And the depth here is 3 now. And now uh, we can see that 1, 2, 3, 4 buckets are sufficient to represent 8 global buckets. And we have saved rehashing costs by rehashing only the things we are splitting. Initially, we could not do that because everything was just one single large bucket, so to speak. But by splitting them into a fixed size smaller chunks, we are able to perform rehashing on those smaller chunks alone and only perform rehashing on the global bin when the smaller chunks need more global bins to be represented. So that's extendable hashing. Uh, so rehashing here will be O of 1 uh, most of the time. Rehashing there in the other methodology would also be O of 1, but the difference here is rehashing is O of 1. Uh, sorry, I mean insertion. Insertion would be O of 1 there and here, but O of 1 remains when local bins are rehashed. Rehashing only becomes O of n when the global bin is rehashed. So this minimizes the amount of the cost of rehashing, given that you're only expanding the local bin, which will be more often than expanding the global bin, right? So uh, rehashing is O of one most of the time, and O of n when expanding the global bin. Insertion is therefore O of one even more of the time compared to the other approaches. Same deal with deletion. So with extendable hashing, you get O of one more the best. Essentially, the best case is more. What do you mean? Probable. So we have insertion in O of one amortized, deletion O of one amortized, and search is also O of one amortized. And search is O of one here because uh, determining the last B bits of a key is O of one, and the local bin is of a fixed size, 3. Searching through 3 elements is also a constant time operation. Searching through a fixed amount of elements is going to be constant time. And that's it for hashing.
Before moving on to sorting algorithms, I just want to explain insertion, deletion, and search in a little bit more detail. So we are computing index based on your key here. This is going to take a constant time. And we are checking if a value already exists at that index. If it exists, we are checking if the key is the same. If the key is the same, then the new value just needs to be updated. So this is just updating the old value to the new value. Otherwise, if the keys do not match, this implies here, this means the keys are not the same, meaning there is a collision here. So, as we have seen just now, it is possible to take this in average cases as O of 1 because more often than not, it is going to be O of 1. Very rarely, it is going to be O of n. So, let's take resolution as O of 1. Uh, and then after resolution, you are just going to insert it at that index. So, this is insertion. Deletion, similarly, you compute your index constant time. You see if there is a value there or not. If a value is not there, then obviously there is no value for that key. So you just return right there. And then you see if the key matches or not. If it doesn't match, again collision resolution. On most cases, it's going to be O of 1. We are just going to take it as O of 1. And then after resolution, you're just going to delete it and return. And then if there was no collision, same thing goes. You just return the value and delete it. All of this again, everything constant time. Searching, same thing goes for computing index, constant time. You check if there is a value. If there is no value, then it is not found. Then you see if the key matches. If it matches, there is no collision. You just return the value as it is. If the key doesn't match, there is collision. Resolution will happen. And then based on if it is found or not after the resolution, you will return the value. Again, we can see that all of this is going to be constant time. Resolution, amortize we take O1. So that is how the different operations work. As Narendra has already explained, we see how rehashing for dynamic hashing, cost is going to be O of 1 when taken amortized, right? And then that is not the only thing the time depends on. So rehashing is one part of it. Uh, collision resolution is also O of 1 here, as already explained before. And hash function, we are making it to be O of 1. If you see here, these are the three things the time depends on. So we can see that for all three operations, search, insert, delete, all these are going to contribute and together it's just going to be O of 1 time complexity. And that is how hash gets the complexity O of 1. Right. Let's move on to count sort. Before we start with count sort, let's see what we already know. We know bubble sort, we know select sort, and we know insertion sort. All these are covered in unit 1. We know heap sort also. Time for all of these are, this is n square, n square, n square. This is n log n. Now we're gonna see count sort in some cases where this performs even better than all the other algorithms we've seen till now, right? So algorithm goes like this. First is step is to find the maximum element, right? Let's do this along with the example. Example I'm taking 2, 5, 3, 0, 2, 3, 0, 3. This I'm taking as my input array, right? Zero, 1, 2, 3. Okay. Finding max, you're going to pass through the array, find the max. Max is 5 here. So we're just going to say, oh, why is it not working? Okay. Max equals 5, right? For this, I'll take time and aux space for each step. Time is O of n for linear search, constant auxiliary space. Then next step is to create a count array creation. Size will be uh, m, the max, right? So we're gonna have count array size will be 5. sorry, m plus 1. Right. Okay, I'll just and time taken, extra space is O of m. Next, we're going to make the count array have the frequency of each of these indices, right? Frequency. So, um, 0 has 1. Okay, let's do it like this. Initially, it's all going to be 0. Uh, update this to 1, and then you go to 5. Update this to be 1. Go to 3. Update this 0. Update this 2. Update this 3. Add 1. 0. Add 1 again. 3. Add 1. Right. So you have counted your frequencies. This is 3, 0. Right. So time taken for this is O of n of 1. Then we are going to take cumulative sum of this count array. So this is going to be changed. So you're just going to sum it at every index. So this is going to be 2. This is going to be 4. This is going to be 4 plus 3, 7. This is going to be 7 plus 0, 7. Be 7 plus 1, 8. Right. So this is going to be your count array now. So let's just forget about this and have this with us. Right. This step took O of m time and no extra space. Last step is to populate the result array with this formula you have to follow. Result of count of ARR of I minus 1 equals ARR of I. This we are going to take uh, from I as decreasing. So we're going to take elements in this array from the opposite direction and apply this formula. So result is going to be an array of same size as the input. So let's create that. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7. Just put these lines. Okay. So let's do this one by one, right? So first, you are going to take ARR of I as 3. So this is going to be count of 3 minus 1. Count of 3 is here, 7. So 7 minus 1, result of 6. You have to put it here. What you have to put? The same value as this. So you're going to put 3 over here. And once you do this, there is one more thing you have to do. you have to decrease count ARR of I. So this index we took, right? This element we took, decrease that by 1. And then we move on to next element. So we are done with this. We will move on to 0. So uh, count of 0, right? Count of 0 is this 2. Count of 0 minus 1 is 1. Result of 1 is where you're supposed to put this number, the one you took from the input array. So 0 will go here, and this one in the count array will be decreased by 1. So this is going to become 1. Right. Then we move on to next number 3. Uh, count of 3 is this 6. 6 minus 1, 5. Result of 5. This here. This is where you're supposed to put this number 3. So 3 goes here. And then you're supposed to decrease this again. So this is going to become 5. Then you're going to move on to this number 2. Count of 2 is 0, 1, 2 here. Let me just remove that. So that is 4. 4 minus 1 is 3. Result of 3. Here you're supposed to put the one you took from the input array 2. Again, let's okay, you're supposed to decrease. I almost forgot. You're supposed to decrease this 4. It became 3 now. And then you will move on to the next element 0. Count of 0 is here 1. 1 minus 1 is 0 here. You're supposed to put what you took here. So this is going to be 0, and then you have to decrease this. So this is going to, it was 1, it is going to become 0. And then you move on to the next element. You are just going to keep doing like this. 3, count of 3, 5. Result of 5 minus 1, 4 is here. You're supposed to put this value 3, and you're supposed to reduce 5. I'll put 4 here, and then I'll go to the next element 5. Count of 5 is 8. 8 minus 1 is 7. So at 7th index I'm going to put this number 5, and then now I have to decrease this. 8 will become 7, and then you're going to move on to the last element. Last element 2. Count of 2 is 3. 3 minus 1 is 2. So in this position, this number is going to go. So 2 will come here, and then this is going to be decreased by 1. So this is going to become 2. So you can see we have finished sorting the entire array. Now you might have this question. Okay, let me just write the complexity here. Result. It took us O of n time, and it took us O of n space. Yeah. So Total time, if you see here, it will become O of n plus m. Arc space also, it will become O of n plus m. You'll ask this question, uh, can't we just make the result just from the frequencies? Why do you even need this cumulative sum? Cumulative sum exists for one reason. It is to make the sort um, stable, right? So what stable means is, if you have this array 5, 3, 1, 3, after you sort it, it's going to be 1, 3, 3, 5. What stable means is, these two elements are of same value, right? But the position of this one comes before this one. So in the sorted array also, the same element has to be before the next instance of that same value. So the value might be the same, but the order of it will be maintained, right? So that's what stable means. Let's see one more term, in place. In place just means sorting occurs within the array itself. From this, we can see that the sorting did not happen within the array itself. It needed to use this to finish doing the sorting. So it is not in place, but it is stable because of this step. We have covered all these algorithms till now. If we see here, we can see that um, bubble sort, selection sort, insertion sort, all of these have average and worst cases in n square complexity only. But we can see that all of these are in place only. Heap sort, it has n log n in all cases. However, auxiliary space depends on whether the same array is used for creation of heap, or if the heap is created separately. Due to how heapify works, this is not a stable sort, and it in place depends whether or not the same array is used. It is possible. Counting sort. Let's see some best case and worst cases. Best case happens when k is almost like it's in the same magnitudes of n, right? So if it's similar or like lesser than n, then this algorithm works in O of n time. So this becomes a very good sorting algorithm for when you have there is going to be like low values. On average, it's going to be n plus k only. Worst case is when k is much greater than n. Obviously, if n is only like some x, and then k is like x cube, you are going to take this much time, which is obviously going to be really bad. So all of this depends on value of your maximum element, right? Space also works similarly like that. It is stable and it's not in place. So yes, that is what I wanted to cover here.